Hello, welcome and lovely greetings to all of you. We are here with another discussion session, and this time the paper is of 4th September 2020 morning shift. The subject, of course, that's physics. Let's begin. The first question, that's from Electrostatics. And let's see, what does the question have to say? There are two intersecting large charged sheets, one having positive, other having negative. The magnitude of the positive density is greater than that of negative. And based on this fact, we need to see the best possible representation of field lines. Now, let me just show you all the corresponding options so that you can have a fair idea. Option 1, 2, option 3 and option 4. So what can we conclude? For that, let me just draw a figure here. So this is one large sheet and intersecting this is another large sheet. Remember, the positive one has a magnitude greater than that of negative. All right. So that's a positive one and this is the negative one. Now there are two things. Let's break down into two segments. The first thing, electric field due to individual sheet would be uniform in magnitude and direction on one side, and on the other side also the same story would be there. So if we just start plotting the field lines in one quadrant, that will give us a fair idea. To do that, let's understand here. First of all, let me finalize in the first quadrant. Due to the positive, the field lines would be away in this way, and due to negative, the field line would be towards. Because the magnitude of this surface charge density is lesser, so this particular vector would be smaller relatively as compared to this. That means the resultant field lines right here is going to be in this way, and the inclination would be somewhat towards y-axis. It would not be at 45 degree, but inclined and tilted towards the y-axis. And because the field contribution due to individual is uniform, so the resultant also has to be uniform in magnitude and direction. While if you see here in the first quadrant, the direction is varying, so this option would be ruled out. Then let me go with second option. Second is a very probable one, and third would be ruled out. But then if you see, because the surface charge density sigma plus is greater, and we have already said that the field lines should have a tilt more towards the y-axis. So between 2 and 4, option number 4 would be the correct one. That was indeed a good one, a very new thought. So for first question, the correct option will be option number 4. Let's go to the second question. The second question is from calorimetry, and have a look. What does it say? The specific heat of water has been given. The latent heat of fusion of ice, that also has been given. We have a mixture having 100 gram ice at 0 degree, and that is placed with 200 gram water at 25 degree. And based on this, we need to calculate the amount of ice that will melt. So the idea is very simple. The heat evolved by water would be absorbed by ice, and that will result into melting of ice, right? So what is the undergoing expression? The first thing is that, let me say, Mi is the mass of ice that will be melted, and in fact, that's what we have to calculate. Multiplied by latent heat of fusion, this will give us the total heat. And this heat which is absorbed by ice is in fact evolved by water, and the mass of water that's given as 200 gram, so that is MW. Just keep in mind, don't confuse this Mi with 100 gram. 100 gram is the total ice, but this Mi is the mass of ice that melts. Let me make it clear here. While this MW is the total 200 gram, specific heat of water multiplied by delta theta, and delta theta will be, of course, will multiply further with 25 minus of 0, isn't it? mc delta theta, the heat lost by water would be used by the ice. So put all the value and be careful with the units. While you solve, you would get 61.7 gram is the total ice that would melt. And option number 4 would be the correct one. Let's go to third question. The third question is from calculation of magnetic field. Let's see what does it say. We have an arrangement and let's try to see this wire A, which is bent in this format. You could see the 90 degrees there and that part is not there. The remaining 3/4 quadrant is there for wire A. And for wire B, the 60 degree portion is not there. So there is the remaining one, the 300 degree, right? Okay, after that, let's see what are the parameters given. Wire A has a current 2 ampere and radius 2 centimeter. So what I'll do is that, let me just write it in terms of variable, IA and RA. Those are the parameters. And let's see, there is another wire B having current a different value. So this will be IB, that's a condition. And the radius of course is RB. All the values are given. It's always advisable that first pick in terms of variable. And after that, we need to calculate the ratio of magnetic fields due to the wire A and B at the common center. So essentially the question is not difficult. It's a regular question where we calculate magnetic field due to a certain arc segment. First of all, how much will be the value of magnetic field due to A? That's going to be, the total angle, its subtends is 3 pi by 2, isn't it? So that's going to be 3 pi by 2 divided by 2 pi into mu naught IA upon twice of RA. That's the magnetic field due to A. What about magnetic field due to B? So that magnetic field due to B, first of all, we need to calculate the angle. And that's 300 degree, okay? And that's going to be 300 multiplied by pi by 180. We've converted into radian divided by 2 pi. So that's going to give me the angle that it subtends. And multiplied by mu naught IB divided by twice of RB. So this is the magnetic field due to B. So here you have BA, BB, all the parameters. You need to divide it and the option will be option number 2. The answer will be 6:5. Okay, now let's proceed to the next question.